if you see it in this, okay, if you see it in this process, in this way, it will be bend like this. Okay, this is one bend and this is another bend. Together, if you're trying to form two bends, okay, then basically toroidal bend does it. Two bends in one shot. Okay, but toroidal bend has limitations. Okay, um, I'll tell you why we use toroidal bend, and simply why not uh, go with just part, so that you can simply if you create this and if you rotate it, automatically you will get a radial tear. Instead, why you're going with the bends and all those things, we'll see. Okay, where is this clear all? Okay, now, so, and you have to remember one thing: if you're giving values within the limit, only then and then only your toroidal bend will happen. Otherwise, it will show an error. So it is little bit difficult one. I don't know where actually they'll be using these options. I too don't know, but it is there in syllabus. So I'm just telling you this. Okay. So I have given some values over here. Click on OK. I'll be going with extrude. Select this. I will be extruding it to 20 mm so that it will be kind of plate kind of. So on this plate, what I'll do, I'll create some indentations like tire. If you see a tire, you will have some indentations, right? The grip are the cuttings which will be there in the tire. I'll be doing some indentations like that. Okay, indentations. I don't know. But, mm, mm, okay, fine. I'll just go with. Okay, excuse me, guys. Not this much. 10 done. Okay, now I'll select this, go to pattern, and pattern I'll be going with direction, and direction I want the first direction to be this. Okay, I want it to be, let us say, 50. I think 50 is going above. Um, 25. The length was 2000, right? Okay. Oh, oh. Okay, more or less. The second direction, select this direction. Okay. Okay. Now I'll go with toroidal. See, the reason why we are going with toroidal bend is whenever you're bending this, whatever these indentations are there, that will also get bent. So that will not happen if you do it in part. Okay. So that is the only reason we'll be using this toroidal bend. Okay. For toroidal bend, there are special requirements. Okay. Go to toroidal blend. Okay. First of all, you are bending a solid, so click on solid. Okay, the second one is you need to define a, uh, a sketch how to bend it. Okay, you need to define a sketch and how to bend it. So in this, the first requirement is coordinate system. Some keep the coordinate system exactly onto this edge. Okay, then go with a line. Okay, I'm just approximately doing everything. I'm not following any dimensions or any sort of thing. And guys, remember, if the bend is not under the limit, it will not take that bend. Okay, it will not take that bend. I'll go with the fillet. Select this. Select this. Okay. Escape. Okay, first let us check whether this will take that bend or not. Yeah, it took that bend. You can see compared to this length, this length will be increased. Why? Because there is a bend. According to the bend, my length is getting increased over on this. Normally, in normal revolve, all those things, this will not happen. So that is the reason. Suppose you want to bend something, and according to that bend, you want to change your indentations. Then only you need to go with toroidal bend. Otherwise, there is no need to use it at all. Okay, this is a little bit complex option. Okay, okay. So bending radius, I can reduce it how much ever I want. I can reduce it. So I'll be going with, it is 12. How much it is? 12,094. I'll just go with 1,000. Let us see how will it react. Whether it will take. Oh, it took surprisingly. I thought it will not take. From 12,000 to direct 1,000 ko gira diya, to I thought okay, I'll just go with 250, 250. No, 250. It is not taking 300 at least. 300 also, it is not taking 450. Come on, dude. Yeah, 450 it took. That means it, whatever the bend radius we are giving, it is beyond its value. Okay, 425, 410, 405, 400, 395, 375. So basically you should know the values. I think you got what toroidal, basically what toroidal bend does. Okay, come here, click on OK. If your values are very perfect, then you can make a total circle here itself exactly, and you can mirror it so that it can become a tire kind of thing. Remember, whenever you are going with toroidal bend, the profile, it should have one axis system over here. Okay, without that axis system, it will not create that bend. Okay, okay. The next and the last option for the part is spinal bend. Okay, we'll see what actually the spinal bend is. So I'll just delete it, delete this. Okay, now we have something like this, and okay, so what I'll do, I'll go sketch on this plane. And always make sure that whenever you're going with for spinal bend, whatever the edges you are giving here, that should be smooth. Otherwise, it will not take that bend. Okay. Make sure that bend is very smooth. Otherwise, that will not. So I have given some fillet, some random sketch, the way I want to bend it. So I have given that. Okay. I think the spinal bend, it should, we should create a sketch inside the bend itself. I'm assuming that. No. Bending geometry, bending spline, error in this. I need to check the sketch once again. Sometimes if that overlap, it will not create. It's good. second. The problem with Creo's interface is this. See, at this intersection, it is not properly showing me the line and all those things. So that is a big problem in Creo. Okay, I'll go with spinal bend, and spinal bend. Okay, then in reference, go with the spine. Generally it should create, but it is not creating, means that is something is wrong with my spine, whatever the sketch I have drawn, right? So something is wrong with that, so I need to go there and edit. I'll try to do it once again properly. Everything got into construction line. I'm assuming this should work out. Spinal bend. Select your bend item. Select your spine. Come on, work it out, work it out, work it out. Yeah. Here you can see the bend, whatever given, we are given, it is not up to the mark actually. So really the bend, whatever I did, it should exactly match with this line. It is showing, it is not matching, it is just offsetting itself. So I don't understand why it is offsetting itself. Okay, let's try it out. Engineering, spinal bend. So whenever I'm selecting this reference, this should not happen. Now, yes, actually there is an arrow. You can see if that arrow, if you see, it is considering this side as fixed, and with respect to this, it is creating this spinal bend. Let's see this arrow, small arrow here. You rotate it, it is exactly matching your. Okay, basically this is your spinal bend. Okay. Okay, guys. With these options, your part is completed. As well as today, we have completed surface as well. Okay, I'll just give a small introduction about sheet metal. For in tomorrow's class, we'll try to go with sheet metal as well. Okay. Um. Okay. I'll just where it is sheet metal. Uh, okay. Okay, guys. So if you see, can anyone say what is a sheet metal? Can anyone explain What is sheet metal? Where we will be using it? Thickness of sheet metal. Why we are using sheet metal instead of casting? With an example. Adil?
The sheet metal thickness ranges from 0.5 mm to 0.6 mm.
0.5 to 0.6. That means only 0.1 mm it will range. It will vary.
Uh, 0.5 to 0.9, I think.
Sheet metal. Okay, above 6 mm it is called as metal plate, and below 0.5 mm it is called as tin foil. Okay, the Coke tin, Pepsi tin are there, right? So they are below 0.5 mm. Okay, basically sheet metal is lightweight and it will give you strength when you properly manufacture it. Okay, it is cheaper in price as well, and you can mold it however you want. That we cannot do in casting process. Okay. Okay, so there is one important what you call property you should know when you are dealing with sheet metal. That property is called as K factor. Okay, Y factor will not be using that much, but we will see what is Y factor as well. So whenever you are bending your sheet metal, can see one area of the sheet metal it is getting compressed, the other area of the sheet metal it is getting expanded. When you bend the sheet metal, the outside it will be getting expanded, the inside it will be getting contraction. Okay, so between this expansion and contraction or stress or strain there will be one neutral point. If you join all those neutral points, you will be getting one thing called as neutral axis. Okay, K factor is nothing but dividing the total thickness of the sheet metal. Okay, by I mean like the distance of the neutral line by the total thickness of sheet metal. You can see T by capital T. You can see small t is nothing but your from the inner surface to the neutral line. Okay, this neutral line, where how it will be formed? See, when you are bending your sheet metal, compression will be formed inside, expansion will be formed outside. So there will be one neutral point. When this compression changes to expansion, there will be one neutral point. You take 100 to 200 sections and join all the neutral points. That is where you will be getting a neutral axis. So if you measure from inner edge to the neutral axis, that is small t, and total thickness is capital T. So small t by capital T will be getting K factor. So why this K factor is important? To measure the workpiece. For example, if you want to create a sheet metal object, first you need to calculate how much area of the sheet metal you want. Then you will cut it, then you will place it in the punch and you will press it. So how much area of the sheet metal you want to calculate it, this K factor is really important. Okay, there is no need for you to calculate here. In the internet, you will have all the what you call values. For this much gauge of sheet metal, what is the K factor? For this material, what is the K factor? All the things you will be getting in the K factor. Okay, smaller the K factor, shorter the flat length. Flat length in the sense, before creating your sheet metal object, what you will do, you'll cut the workpiece from your roll, the sheet metal roll, and you will try to that how much you want to cut. That is called as flat length. So shorter the K factor, shorter the flat length, higher the K factor, higher the flat length. Okay. K factor comes into a ratio of neutral radius or neutral axis divided by the thickness of the material. In prepared charts, usually the value varies between 0.3 to 0.5 mm. Okay, generally people will consider 0.5 mm, but it is a theoretical value. They are assuming that this neutral axis comes exactly in the middle of the thickness, but in real time scenario that is not the case.
Okay, generally 0.393445 like that will coming, or sometimes it may come, if you're lucky enough, it may come to 0.5 as well. Okay. Okay, y factor is dependent on k factor. The y factor formula is y factor is equal to k factor into pi. This is not required, I'm just giving you an extra information. Okay, so generally it becomes, so whenever you're starting your sheet metal option or sheet metal operation, first thing you should enter is your k factor and your thickness of the material. These two will be constant all along your part. Okay, tomorrow we'll see how we can enter those things. Okay, that k factor and y factor makes bending more precise without damaging the material. Okay, once you know the k factor, you know, okay, how much bend, how much angle bend I can take, how much sharp bends I can take. All those things you will get to know when you are having k factor, when you know the k factor. Okay, knowing the K factor identifies the location of your neutral axis after bending and additional material elongates. I told you, right? One area is getting contracted, another area is getting expansion. Okay, how much area, if you bend this much of angle and this much of K factor, how much length it will elongate? That also you can calculate with the help of K factor. So remember, whenever you're going with sheet metal, two, four, actually there are three important things.